Dear friends, our today's subject is digital system design, and topic we will discuss in this video is combinational circuit design. So at the end of this video lecture, you will be able to design a combinational digital circuit. Let me first define what is the combinational digital circuit. So any digital circuit or any digital logic circuit, it's either a combinational digital circuit or a sequential digital circuit. Let's define what is the combinational digital circuit. So combinational digital circuit, it is defined as if the present output, if the present outputs is depends on only present inputs, then such circuit it is called a combinational digital circuit. In a sequential digital circuit, present outputs is depends on present inputs as well as previous outputs or previous states. Such circuit it is called a sequential digital circuit. So in a combinational digital circuit, there is no any feedback path or a feedback loop, as well as in a sequential digital circuit that should not be having any memory elements. In case of sequential digital circuits, it's have a feedback loop as well as it may have the memory block or the memory elements to store the previous output, to store the previous states. So this is the difference between a combinational and a sequential digital circuit. In this video lecture, we will learn how to design a combinational digital circuit. So let's first start with the steps to design a combinational digital circuit. So it is called a design procedure. Design procedure for a combinational digital circuit or a design steps, right? So first step to design a combinational circuit is state the problems. So first them is the problem is stated, means the problem given in terms of some statements. Second step is, from the problem statement we have to identify identify numbers of inputs and outputs variable required. Numbers of inputs and outputs variable required from the problem statements. Third step is, once we identified number of inputs and outputs variable, third step is give the name of give name of each input and output variables with some letter symbol. Fourth step is, after giving the inputs and outputs with the letter symbol, fourth step is prepare truth table which shows the input and output relationship as per the problem statement. So we have to prepare a truth table. The definition of truth table is all the possible combination of input variables and its corresponding desired output as per the problem statements. So if there are three inputs variable, then possible combinations are 8. So we have to write all the possible combination of input variables, and for each combination what is our desired output as per the problem statements that we have to prepare. It is nothing but the truth table. Fifth step is minimize 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 each output variable, each output variables using any minimization techniques, using reduction techniques. And so after the fifth step we will get the output. Each output variable is a function, as a truth table of in terms of input variables, right? Minimize the Boolean equation will get after the fifth step. Sixth step is implement each minimized output Boolean functions. Implement a output variable or a Boolean function, minimize the Boolean function, Boolean equation using different logic gate, different logic gates. Okay? So these are the steps to design any combinational digital circuits, right? So it is designing. It start with the problem statement, and at the end we will get a circuit which have the logic diagrams. At the end we'll get the input and outputs. It's the transfer function in the form of a logic diagram, right? So let me design. Let's take one example to design a half adder. Let me take one example. Let me design a half adder. Right? So when we design any combination circuit, it's have some practical constraints. So let me, before designing a half adder, let me discuss what are the different practical constraints. Practical constraint. Let me discuss different practical constraints before designing a combination circuit. What are the different practical constraints? Right. So first is once we uh, once we design, it should have, the design should have a minimum number of logic gates. We have to design a combination circuit such a way that it required a minimum number of logic gates. So this is first practical constraints, right? We have to keep in our mind when we design any combination circuit, it should require minimum number of logic gates. It should not have any redundant logic gates, extra or redundant logic gate, right? Second constraint is minimum number of inputs to any gates. We have to design a circuit such a way that it's have a minimum number of inputs to any gates in a design, right? So minimum number of inputs, these have a 3 input and gate, like that we have to minimize the number of input. If our design can possible to implement using the 2 input and gate, do not use the 3 input and gates, right? So it is called a fan in. We have to minimize the fan in. Third thing is we have to keep in our mind, it is minimize, or it should design should have a minimum number of outputs drive by any gates. So output of any gate, right? This is output of any gates if we required to give the input of different gates, right? So we have to minimize this outputs, that we have to give this output to a different gate. We have to minimize this. It is called a fan out parameter. So it is called a driving capability. We have to reduce the to connection of output of any gates to a input of a different gates. So we have to design such a way that it should minimize this. Fourth thing is we have to design our combinational circuit such a way that it should have a propagation delay. Minimum propagation delay. So minimum propagation delay means the time required to propagate the signal from input to output. It is called a propagation delay. Right? Fifth things we have to keep in our mind, it is our design should have a minimum number of interconnects. Interconnects. So we have to design a combinational circuit such a way that it should have a minimum number of interconnects. So these are the different practical constraints when we have to keep in our mind when we design any combinational digital circuits. Right? So let me take the example to design a half adder and we'll proceed. For the half adder, we'll do all the steps. So you'll get clear idea how to design any combination circuit. Half adder. So first of all, let what is the definition of half adder? So half adder, it is called a 2-bit adder. It is called a half adder, right? So if we want to add any 2 bits, suppose one bit is uh, A, if I want to add with another bit of B, this is called a half adder, right? So suppose I want to add, suppose A is 1 and B is 0, suppose I want to add this, is called a half adder, right? So this is the definition of half adder. Now we have to decide this half adder, it is a combinational circuit or a sequential circuit. So half adder, it is a combinational circuit because the present outputs, it not depends on the what is the previous input. It depends only on the present inputs. Suppose present input A is 1 and B is 0, so it produces the output is 1 irrespective of the previous inputs or the previous outputs. So half adder, it is a combinational digital circuit. Second step is we have to identify the number of inputs and outputs required. So here we want to add the 2 bits, so definitely we require the 2 variable as an input. So this is the half adder in which we want to add the 2 bit, one is A and another is, let's see, it is a B. To add the 2 bit, what is the possibility of a maximum output variable required? So if you want to add the 2 bit, let's take the maximum value. So A maximum is 1 and B is also maximum is 1. So if we add the 1 plus 1, when both the input have maximum value, at that time, let's see, so sorry, so what should be the output? So here 1 plus 1, let's do the binary additions. So 1 plus 1 in a decimal it is 2, and how to represent the 2 in a binary? It is a carry is equal to 1 and some bit is equal to 0, right? So if we add the 2 bit, we require at max the 2 output variable. So in this design, we require the 2 output variable that we call one output variable as a sum and another output variable that we call it is a carry. So in half adder, we require the 2 input variable and the 2 output variables. Let me give the name. Next step is to assign the different letter symbols of inputs and output variables. So here we have assigned the letter symbol of inputs A and B, and for the output at sum bit and the carry bit. Right. Third step in any design is to prepare the truth table. To prepare the truth table. Let me prepare it's a truth table. Truth table. So as per the definition, what is the truth table? So truth table is have a all possible combination of input variables. So here we have the 2 input variable A and B. So for the 2 input variable, how many possible combinations? So for the 2 input variable have the 4 possible combinations 0 0, 0 1, 1 0 and 1 1. And for each possible combinations, we have to find out the output as per the problem statements. So here output is 2 variable, one is sum and another is carry, right? So if we add the 0 plus 0, so if we add a 0 plus 0, what should be the our sum bit? 0 plus 0, sum bit is 0 and carry is also 0. So sum bit is 0 and the carry bit is also 0. If we add the 0 plus 1, if we add the 0 plus 1, then 0 plus 1 is 1, so sum bit is 1 and the carry bit is 0. So sum bit here it is 1 and the carry bit is equal to 0. Now third combination is 1 plus 0. So let me add 1 plus 0. So 1 plus 0 it is equal to 1 and the carry bit is equal to 0. So 1 plus 0 sum bit is again 1 and carry bit is equal to 0. Now if we add the 1 plus 1, then 1 plus 1 it is equal to 2 and the sum is equal to 0 and carry is equal to 1. 2 can represent in a binary is 1 0. So it produces the sum bit is equal to 0 and the carry bit is equal to 1. So this is the truth table how to prepare from the problem statements, right? So once we prepare the truth table, next step in a combinational circuit design is minimized or prepared the Boolean equation of each output variable. Prepared a minimized Boolean equation of each output variables. So here we have a two output variables, sum and carry. So let me prepare its minimize the Boolean equation of sum and carry. Here we use a Karnaugh map to minimize the output variable. So let me write again the truth table of half header. So I have two input and it produced a two output 0 1. It is 1 0 1. Sum is equal to 1 and carry is equal to 0. For the input 1 and 1, sum is equal to 0 and carry is equal to. Now let me prepare the for the S. Let me prepare the Karnaugh map. So here the input variable are two. So Karnaugh map it is a two variable Karnaugh maps. So for the two variable Karnaugh map and it is a function of S. Right. So let me take as a different row as a MSB variable A. So here it is A bar and here it is A. And for the different column, let me use the variable B. So it's B bar and B. So this box it is for the midterm 0 because A bar B bar and this is A bar B. So midterm 1. This is for the midterm 2. It is 1 and 0. So midterm 2 and here it is A and B are 1 1. So it is for the midterm 3. Right. Now next step is to map from the truth table to the Karnaugh map. Right. So for the midterm 0, when A and B are 0 0, then what is the sum bit? So sum bit is equal to 0. So we have to map this 0 here. Right. Now for the input is 0 and 1 means the midterm 1. For the midterm 1, what is the sum bit? Sum bit is equal to 1. So this 1 is mapped here. Right. Now for the midterm 2, when A is equal to 1 and B is equal to 0, what is the sum bit? Sum bit it is equal to 1 and this one is mapped here. This one is mapped here in the Karnaugh map. And when the A and B are the 1 1 means the midterm is equal to 3 and for at that time sum bit is equal to 0. So this 0 is mapped here. Right. So this is mapping of a truth table to the Karnaugh map. This is the mapping of truth table to the Karnaugh map. After the preparing the Karnaugh map, we have to start making the group of ones. Group of ones. So we'll get the minimized Boolean equation of a function S. Right. So how to minimize the Karnaugh map? We know very well. Let me repeat here. So when we start to minimize the Karnaugh map, have the rules we have to check. First rules is to minimize using Karnaugh map. First rules is we have to cover all the ones. All ones have to be covered in a group. Second rule is we have to cover all the ones with minimum number of groups with minimum numbers of groups. So definitely if you want to cover all the ones with a minimum number of groups, definitely we need to be have the group size is maximum. So group size should be maximum. So with a maximum group size, group size with a maximum group size, right? So when we go for the K-map reduction, we have to keep in our mind we have to cover all the ones, and we have to cover one with a minimum number of groups, and we have to maximize or a maximum group size, right? So and in a group we should have only ones, that should not be any zero inside the group. So let me start for this one. Let me do this process for this one. So how we have to start with the maximum group size. Right? So for this one, let me check the group. This Karnaugh map, it is a two variable Karnaugh map. So maximum group size is 4. So let me check for this one, group size 4 is possible or not. So definitely not, because it include the 20. So it cannot possible to make a group of 4. Group of 4 is not possible, then we have to go one step down. Let we have to check the group of 2 is possible for this one or not. So group of 1, group of 2. So for the group of 2, this is one possible for the group of 2, but it's have the 0. It include the 0. So and another possibility of group of 2 is this min term 1 and 3, but it's also include the 1 0. So group of 2 is also not possible in this case. Then we have to check the group of 1. So definitely itself is a one of the group of, right? Once we complete this process, then we have to do the same process for the remaining ones. Remaining ones in a Karnaugh map. So remaining ones for this Karnaugh map, it's only one, min term 2 present in min term. Now again we have to start a group of 4 is possible for this one. No. Group of 2, it is not possible. This is also not possible. So group of 1. Right? After once all the ones are covered, stop to preparing the extra group, because our third is we have to cover all the one with the minimum numbers of groups. So do not prepare the extra group, right? So let's write what are the common variable in each group, right? So in this group, common variables are a bar and b. So first is a bar and b. And for the second group, its a common variables are a and b bar. A and b bar. So a and the b bar. So this is the minimize the Boolean equation of a one of the output variable. It is a sum bit. Similarly, we have to prepare for the another output variable, and another output variable here, it is a carry bit. So we have to prepare a Karnaugh map for the carry bit. So carry here the input are the 2. So it is a 4 variable Karnaugh map, and that we use the A as a for the different rows and for B as a different column. So this is min term 0, min term 1, min term 2 and min term 3. Let me map from the 2 table to the Karnaugh map. So min term 0, when the A and B are the 0 0, at that time carry bit is equal to 0. So here it is a 0. When min term 1, when A is equal to 0 and B is equal to 1, at that time carry bit is equal to 0. So this 0 is mapped here. When the A is equal to 1 and B is equal to 0, then carry bit is again 0. So this 0 we have to map here. And for the when A and B are the 1 and 1, at that time carry is equal to 1. So we have to put the 1 in the min term box. Right? Now we have to start minimize the using K-map. So our aim is to cover all the ones. So let me do this process for this single ones. We have single one in this carry Karnaugh map. So let me see for this one group of 4 possible, not. It include the 0, so group of 4 is not possible. Let me check for this one group of 2 is possible. No, it's also not possible. So make a group of 1. So let me write the minimized C. So it's have a single group, and let write this common variable in this group. So from the row it is A, and from the column it is B. So common variables are A into B. Right? So this is the another minimized Boolean equation of another output variable. It is a carry bit. It is a carry bit. Okay? After finding the minimized output Boolean equation, next step is to implementation of minimized output variable. Minimize the output variable. So here first it can be implemented using the different circuit topology, and we have to choose as per our practical constraints, as per the specification, which circuit if we take will that will satisfy the practical constraint or it satisfy the specifications, right? So this can be implemented is one circuit is A, and we required one is A, and another is bar is A bar is also required for some bit. So let me prepare one line for A bar, and one is B, and B bar is also required for the sum bit. So let me invert it. Now first is A bar into B. So A bar into B, that can implement A bar, and here it is, from here it is B, and ending of A bar and B. So here we'll get A bar into B. Another product term we required is A into B bar. So A into B bar. So another product term will get A into B bar, and that we have to OR this both the product term we have to OR for the sum output. It produced our S, right? Similarly for the carry it is A into B. So here it is A, and from this is B, ending it produced A into B, nothing but our carry out. So this is one of the circuit we can implement for the half adder, right? Another is this sum bit is, here it is A bar into B plus A into B bar. It is nothing but the XORing of A and B, and carry it is A and B and D. So another circuit we can use the two input XOR to implement a sum and two input AND to implement the carry. So this is the another topology or another circuit diagram to implementation of an half adder, right? Let's see have some practical constraints for the implementation is to minimize the propagation delay. So let me check the propagation delay in the both the circuit. So let's suppose the propagation delay of XOR gate is suppose 20 nanosecond and propagation delay of AND gate is suppose 15 nanosecond. So the propagation delay for the sum output bit it is a 20 nanosecond, and the propagation delay for the carry output bit it is a 15 nanosecond delay. So average propagation delay, that means the maximum propagation delay is considered as a propagation delay of the circuit. So propagation delay of this circuit is for the half adder, it is a 20 nanosecond if we implement using this topology. Let me check for the previous topology. So in a previous topology, suppose the propagation delay of a NOT gate, it is suppose 5 nanosecond. Suppose propagation delay of AND gate is 15 nanosecond. And suppose propagation delay of OR gate is 10 nanosecond. Right? Then what is the total propagation delay for the sum bit? It is 5 nanosecond of NOT and then 15 nanosecond of and then 10 nanosecond for the OR gate. So total is 5 plus 15 plus 10 for the OR gate. So for total propagation delay for the sum bit is 30 nanosecond delay, and for the carry propagation delay is only a 15 nanosecond. So the this topology circuit propagation delay, it is a maximum of these two, so it is 30. So circuit propagation delay is the 30 nanoseconds, because here in this topology have the maximum number of cascading stage. Output of one is given to another and output of another stage given to third stage, and that produce the final output. So in this topology have the maximum number of cascading stage, which will increase the propagation delay. So if we implement a half adder using this topology, then it will have the more propagation delay compared to implementation of another topology which have the less propagation delay. Right? So this is the different constraints it's given in a problem statement in a designing of any combinational circuits. Let's take one more example. It is a full adder. Let me design a full adder. Another example is full adder. Let first define what is the full adder. So definition of full adder is it is a 3-bit adder. 3-bit adder, it is called a full adder. So it's have the A suppose 1 bit, B suppose second bit, and C suppose third bit. It is an addition of 3 bits. Right? This is 3-bit adder, so definitely the inputs variable are 3. Now we have to find out what are the output variable required. So full adder is it is the 2-bit adder plus the previous carry. It add the previous carry. So when we are adding the that number, suppose it have 4-bit number addition with another 4-bit number if you want to add, then suppose whatever the output of this, suppose here is 1, suppose here it is 0, so it is 1 and the carry is equal to 0. So 0 plus 1, it is sum bit is 0 and it propagate the next stage carry is 1. So full adder it is required when we want to add the 4 bit with another 4 bit or the 8 bit with another byte addition, like that. So we require this 2-bit add with the previous carry. So we need to add at least the 3 bits that include the previous carry. Right? So in a full adder, it's have the 3 inputs. Now next step is we have to identify how many output variables required. So let me take the maximum value of each input variable. That will give the maximum output range or maximum output digit. Right? So let give A is equal to 1, B is equal to 1, and previous carry is also equal to 1. Then if we add this 3 bit, 1 plus 1 plus 1, it is equal to 3, and 3 can represent in a binary, it is a 1 and 1, 1 and 1. So we required a 2 output variable. To add the 3 bit, we required max a 2 output variable. So in a full adder, it's have the 3 input variable. Let me give the name A, B and C, and it's have a 2 output variable. One is the sum bit and another is the carry out bit. Right? So this is the full adder which have the 3 bits are input and 2 bits are output, and we have given the name of each input and output variable. A, B, C are the input variable name, and S and C0 are the output variable name. After giving the name, next step is to prepare the truth table. Next step is to prepare the truth table. So let me prepare the truth table. So we know it's have a 3 input variable truth table. So it's have a 3 input variable A, B and C. So total possible combinations are 8 for the 3 variables. One is 0, 0, 0, another is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1 and 1. So there are 8 possible combination of 3 input variables. Now we have 2 output variable, one is sum, another is carry out. Sum and carry out. That we have to find out from this as per the definitions. So if we add 0 plus 0 plus 0, so if we add 0 plus 0 plus 0, it's have a 0 and 0 can represent in binary 0 and 0. So sum bit is 0 and the carry bit is also 0. If we add the 0 plus 0 plus 1, so it is a 1 and 1 can represent the 0 and 1. So carry is equal to 0 and sum bit is equal to 1. 0 plus 1 plus 0, so it is again 1. So sum bit is equal to 1 and carry bit is equal to 0. 0 plus 1 plus 1, so it is 2 and 2 represent as carry 1 and sum bit is equal to 0. 1 0, it is a representation of 2. And 1 plus 0 it is 1, so sum bit is equal to 1 and carry bit is equal to 0. 1 plus 0 plus 1 2, so sum is equal to 0 and carry is equal to 1. 1 plus 1 plus 0, so it is 2, so again sum bit is equal to 0 and carry bit is equal to 1. And 1 plus 1 plus 1, it is 3 and sum bit is equal to 1 and carry bit is also equal to 1. So after preparation of truth table from the problem statement, we have to minimize each output variable. Next step is to minimize each output variables. So here we have a 2 output variable and the input variable are 3. So it have the 3 variable Karnaugh map. So let me prepare a 3 variable Karnaugh map. We'll use a 2 variable for 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 column and 1 variable for row. So A bar and here the B bar, C bar, B bar C, B C and B C bar. Right? So first box it prepared the min term 0, min term 1 and here it is min term 2, min term 3, min term 4, min term 5, min term 6 and min term 7. Let me map from the truth table to Karnaugh map. So for the min term 0, the sum bit is equal to 0. So here it is 0. For the min term 1, sum bit is 1. So here we have to put the 1. Here for min term 2, sum bit is equal to 1. So in a min term 2, we have to put the sum bit is equal to 2. For the min term 3, sum bit is equal to 0. So here it is a sum bit is equal to 0. For the min term 4, sum bit is equal to 1. So here we have to put the sum. For the min term 5, sum bit is 0. So here it is equal to 0. For the min term 6, sum bit is 0. So here min term 6, sum bit is equal to 0. And for the min term 1, sum bit is equal to 1. So here it is a 1. So after the mapping, we have to minimize this Karnaugh map. So we have to try to cover all the one. We have to cover all the one with the maximum number of groups, minimum number of groups with the maximized size of the group. So let me start for the midterm ones. So for this one, we have to check the group of 8 is possible or not. So here group of 8 is not possible. Now we have to check for this one, group of 4 is possible for this. So group of 4 is also not possible. Now for this one, we have to check the group of 2 is possible. This is one of the possibility of group of 2 is not possible. Here is another possibility. This is also not possible. This is third possibility. It is also not possible. So group of 2 is also not possible. Then we have to check the group of 1. So group of 1 it is 1. Similarly for this one, group of 8 not possible, group of 4 is also not possible, group of 2 is also not possible. So make the group of 1. For this one, group of 8 not possible, group of 4 not possible, group of 2 is also not possible. So make its group of 1. For this one, group of 8 not possible, group of 4 is not possible. So group of 2 is also not possible. So make its group of 1. So in this some bits have the 4 group and each group size is 1. Right? So here let's write the common variable. So from this a bar, b bar and c. So from the first group the common variable are a bar, b bar and c. From the second group common variable are a bar, b and c. A bar, b and c bar. From the third group common variable are a, b bar, c. A, b bar, c bar. And from the fourth group common variables are a, b and c. A, B and C. Right? So this is the minimized Boolean equation of the sum output variable. Right? That can be right in terms of XORing like that. If you can take the A bar is common from the first two terms, then in bracket it is a B bar C plus B into C bar. And from the last two term, let's take A common, then in bracket it is a b bar c bar plus b into c. Right? So a bar, this is nothing but the b and c XORing. This is the equation of XORing plus this is the equation of XNORing. XORing, here it is XNOR. This b and c. Right? So we know the XNOR is the complement of XOR, so it can write B XOR C. It can write here the complements of. Let's take the Z is equal to B XOR C, and we can say then it is A bar into Z plus A into Z bar. Right? So this equation is nothing but the XORing of A and Z. Substitute the value of Z, then it's have the A XOR B XOR C. So sum bit it is nothing but the XORing of all the three inputs. Let's find the what is the carry. Then let me similarly prepare the Karnaugh map for the carry out. So for the carry, let's prepare the Karnaugh map. It is an three variable Karnaugh map. A bar A, B bar C bar, B bar C, B C, B C bar. Right? Let me map the two table to the Karnaugh map. This is for the min term 0, so it is 0. In a min term 1, it's also 0. In a min term 2, it's 0. In a min term 3, here the 1. And min term 4, it is 0. Min term 5, it is 1. Min term 6, it is also 1. And min term 7, it's also 1. Right? Let me minimize this. For this one, group of 8 is possible, not possible. Group of 4 is possible. Let me check the possibility of group of 4. So group of 4 is also not possible. Let me check the group of 2. Yes, group of 2 is possible. So make the group of 2. Let me check the uncovered one. So this is one of the uncovered one. For this one, let me check the group of 8. Group of 8 is not possible. Let me check for this one. Group of 4 is possible. No, group of 4 is also not possible. Let me check the group of 2 is possible. Yes, this group of 2 is possible. We can use the covered one to maximize the group. Right? This one is already covered, but we can use that covered one to maximize the group, which minimize the literal, which minimize the number of variables. Now let's check for this uncovered one. Group of 8 is not possible. Group of 4 is also not possible. Let's make the group of 2. So in this C have the three product term, and each product term have the group of 2. So let me write from this. Common is A and C for this B and C, and for this product term A and B. So for the carry, it is A into C plus B into C plus A into B, and for the sum bit, it is A XOR B XOR C. Yeah, next step is to implementation, right? So here the implementation, first logic implementation of sum, it is an XORing of A and B. So let me use the two input XOR, right? A and B is first XOR, and it is XORed with the C. So we'll get the final sum. It is an XORing of A, B and C. Then for the carry, it is an first is the ending of A, B, A and B, and another product term in a carry, it is a B and C. Third product term in a carry, it is an A and C. And its ORing, it produced the carry bit. So this is one implementation diagram to implementation of an full adders. Now here the carry also we can produce from the sum bit. It is like the carry we can write C. Another way we can write the carry, it is Z, which is third bit, which it is C out, carry out. So carry out is C XORing with A and B. A and B plus A into B. Right? This also we can write the carry. Right? Let me prove this carry out. It is equal to A into B plus B into C plus C into A. Right? So let me distribute it. So A XOR B can write A bar B plus A B bar. Right? Let me multiply the C. So it is C A bar B plus C A B bar plus A B. Right? Let me take a B common from first and last term. Then it is A C bar plus A, and this C A B bar as it is. Now we know A C bar plus A, it can write A plus C. Right? So this is AB plus BC, and last term C A B bar. Now let's take the C common from the last two term. So here B plus A B bar, and we can write B plus A B bar is B plus A. So here it is AB plus BC plus AC. It is same as this. So another way we can implement the carry, it is C into the XORing of A and B plus A into B. Right? So how to prepare the second is, here you will get the A XOR B. This is the A XOR B. So this A XOR B, it end with C. So we'll get the A XOR B with ending, plus another ending is A and B. And ORing of these two will produce the carry out. So another logic of carry output that can use A XOR B, which is produced in a sum. Right? So this is the another implementation of a full adder logic diagram. Hope it's clear, and hope you have enjoyed this video. Thank you.